Wormholes represent one of the most captivating predictions of Einstein's general relativity, theoretical tunnels connecting distant regions of spacetime, offering shortcuts across the cosmos and perhaps even through time itself. These mathematical structures emerged from equations describing how massive objects warp the fabric of space and time, yet their physical existence remains one of astronomy's greatest mysteries, sitting at the boundary where mathematics meets the unknown, where human imagination reaches toward possibilities that may or may not exist in our universe. Welcome to another journey through the cosmos. It's wonderful to have you here tonight. Before we begin, find yourself somewhere comfortable, somewhere safe, somewhere where the weight of the day can finally lift from your shoulders. Perhaps you're nestled in bed, blankets pulled close. Perhaps you're in a favourite chair, the room softened by dim light. Wherever you are, allow yourself to settle. If you enjoy these explorations and would like to hear more, a like and subscribe helps this channel continue its quiet journeys through the mysteries of the universe. To those already subscribed, thank you. Your presence means more than words can express. Tonight, we'll drift through the complete story of wormholes, from their birth in mathematical equations to modern searches using gravitational wave detectors. We'll move slowly, gently, letting each idea unfold at its own pace. There's no rush, no urgency, just the soft unfolding of one of physics' most beautiful mysteries. So settle in, close your eyes if you'd like, and let's begin our journey through the tunnels of spacetime. In the early decades of the 20th century, physics underwent a transformation so profound that our understanding of reality itself changed forever. At the centre of this revolution stood Albert Einstein, a patent clerk turned physicist whose imagination could see beyond the limits of everyday experience. In 1915, Einstein published his general theory of relativity, a mathematical framework that reimagined gravity not as a force pulling objects together, but as the curvature of spacetime itself. Imagine spacetime as a vast fabric, smooth and flat when nothing disturbs it. Now place a massive object, a star or planet, onto this fabric. The object's mass creates a depression, a curve in the material. Smaller objects nearby naturally roll toward this depression, not because they're being pulled by some invisible force, but because they're following the curves in space-time itself. This was Einstein's radical insight. Matter tells space how to curve, and space tells matter how to move. The mathematics Einstein used to describe this warping of space-time were extraordinarily complex. A set of equations known as the Einstein field equations. These equations relate the geometry of spacetime to the distribution of matter and energy within it. Solving these equations for different configurations of mass and energy reveals how spacetime curves in response, and thus how objects move through that curved landscape. Within months of Einstein publishing his theory, physicists began exploring its implications. One of the first was Carl Schwarzschild, a German astronomer and physicist. In 1916, while serving in the German army during World War I, Schwarzschild found an exact solution to Einstein's field equations. His solution described the space-time geometry around a non-rotating, spherically symmetric mass. This would later be recognized as describing what we now call a black hole, though that term wouldn't be coined for decades. Schwarzschild's solution was remarkable for its mathematical elegance, but it contained something puzzling. The equations described not just the region around the massive object, but seemed to extend into two separate regions of space-time. Picture it like this. If you could somehow visualize the curved space-time around a black hole, you'd see a funnel-like depression extending downward. But Schwarzschild's mathematics suggested there might be two such funnels, connected at their narrowest points. This strange double funnel structure caught the attention of Austrian physicist Ludwig Flamm. Later in 1916, Flamm was studying Schwarzschild's work when he noticed this curious mathematical feature. The equations seemed to permit a bridge-like connection between two different regions of space. Flamm described this as potentially connecting our universe to a white hole, a theoretical opposite of a black hole that could only emit matter and light, never absorbing them. At the time, this seemed like nothing more than a mathematical curiosity. The solutions were valid according to Einstein's equations, but whether they represented anything real remained unclear. The general theory of relativity was still new, and physicists were just beginning to explore its implications. Many of its predictions seemed strange, almost impossible, yet time and again observations would confirm Einstein's mathematical visions matched reality. The fabric of space-time, as Einstein described it, wasn't the rigid, unchanging stage that Newton had imagined. It was dynamic, flexible, capable of rippling and warping in response to matter and energy. Light itself would bend around massive objects, following the curves in space-time. Time would run slower in strong gravitational fields than in weak ones. These predictions seemed outlandish, yet astronomical observations began confirming them one by one. In this new understanding of gravity, space and time were no longer separate entities. They were woven together into a four-dimensional continuum where the 3 dimensions of space and 1 dimension of time merged into a unified whole. An event in this space-time had not just a location but also a time. The path an object follows through space-time is called its world line, a track through 4 dimensions rather than just 3. This union of space and time had profound implications. If space could curve, and if space and time were unified, then time itself could curve. The geometry of space-time could twist and loop in ways that had no equivalent in ordinary 3-dimensional space. This mathematical flexibility opened doors to possibilities that seemed to belong more to science fiction than to serious physics. Among these possibilities was the idea that space-time might contain shortcuts, paths that would allow you to travel from one point to another without crossing all the space in between. Imagine folding a piece of paper so 2 distant points touch. In the flat, unfolded paper, those points are far apart. But in the folded configuration, they're adjacent. If you could somehow travel through that folded connection, you'd bypass the distance that normally separates them. This is the essential concept behind what would eventually be called a wormhole. The term itself wouldn't appear for decades, but the mathematical seeds were planted in those early explorations of general relativity. The equations permitted these bridge-like structures, these connections between distant regions of space-time. Whether nature actually created such structures remained an open question, one that would tantalize physicists for generations. The early years of general relativity were filled with such discoveries. Each new solution to Einstein's equations revealed another surprising possibility. Some solutions described expanding universes. Others described rotating masses that dragged space-time around with them. Still others described regions where space-time curved so dramatically that not even light could escape. The theory was rich with predictions, each stranger than the last. Yet for all its strangeness, general relativity worked. Observations confirmed its predictions with remarkable precision. The theory explained the precession of Mercury's orbit, a tiny discrepancy that Newtonian gravity couldn't account for. It predicted that light from distant stars would appear to bend around the sun during a solar eclipse, and measurements during the eclipse of 1919 confirmed this prediction, making Einstein an international celebrity overnight. As physicists gained confidence in general relativity, they began taking its more exotic predictions more seriously. If the theory could accurately describe the motion of planets and the bending of starlight, perhaps its predictions about the deeper structure of space-time deserved attention too. Maybe space-time really could form these bridge-like connections. Maybe these mathematical curiosities corresponded to actual physical structures. The stage was set for deeper exploration. The mathematical framework existed. The conceptual foundation had been laid. What was needed now was for someone to take these ideas seriously, to explore them not just as mathematical exercises, but as potential features of our universe. That someone would be Einstein himself, joined by a colleague in a collaboration that would give these bridge-like structures their first formal treatment. The year was 1935. Einstein was at the Institute for Advanced Study in Princeton, working alongside Nathan Rosen. Together, they would write a paper that, while initially intended for a completely different purpose, would plant the seeds for our modern understanding of wormholes. But to understand their work, we need to understand the puzzle they were trying to solve. By 1935, Albert Einstein had been wrestling with quantum mechanics for years. He had contributed to its early development, but as the theory evolved, he grew increasingly uncomfortable with its implications. Quantum mechanics described the subatomic world as fundamentally probabilistic, where particles didn't have definite properties until measured. Einstein found this deeply unsatisfying. He believed there must be a deeper, more complete description of reality underneath the quantum uncertainty. One aspect of quantum theory that particularly troubled Einstein was the concept of point particles. In quantum mechanics, fundamental particles like electrons were often treated as mathematical points with no spatial extent. Yet these point particles had mass and charge concentrated in zero volume, creating what physicists call singularities, places where mathematical quantities become infinite. Einstein felt these singularities were a sign that something was missing in our understanding. He began searching for a way to describe particles without singularities, a theory where the electron and other fundamental particles would emerge naturally from the geometry of spacetime itself. If matter could curve spacetime, as his general theory of relativity showed, perhaps the reverse was also true. Perhaps what we call particles are actually features of spacetime geometry, regions where space curves in particular ways. Einstein enlisted the help of Nathan Rosen, a young physicist also working at the Institute for Advanced Study. Together, they explored whether solutions to the field equations of general relativity could provide a model for particles. They wanted to see if they could describe an electron as a bridge in space-time rather than as a point with infinite density. In working through the mathematics, Einstein and Rosen examined the Schwarzschild solution that described the geometry around a spherically symmetric mass. This solution had that curious feature Flamm had noticed years earlier. The equations seemed to describe two separate regions of spacetime connected by a throat. Einstein and Rosen realized they could use this structure as the basis for a model of particles. Their key insight was to match two sheets of spacetime, effectively creating a bridge between them. Imagine two separate flat sheets. Now imagine cutting a hole in each sheet and connecting them with a tube, like a tunnel linking two surfaces. The tube itself has a throat, a narrowest point where the two sheets connect. This throat would have some radius, some finite size, meaning there would be no singularity, no point of infinite density. Einstein and Rosen proposed that this bridge-like structure could represent a particle. The mass of the particle would be related to the geometry of the bridge. There would be no point-like singularity because the bridge would have a throat of finite size. From the outside, observing from either of the two sheets, the structure would appear as a region of concentrated mass and charge, behaving much like a particle. They published their paper in 1935 with the title "The Particle Problem in the General Theory of Relativity." In it they wrote that it is shown that physical space, as conceived in this paper, possesses a two-sheet structure. This two-sheet structure, connected by what they called a bridge, was their solution to the problem of singularities. The Einstein-Rosen bridge, as this structure came to be known, was a valid solution to the field equations of general relativity. The mathematics worked perfectly. The bridge existed in the equations, a tunnel-like connection between two regions of spacetime. It represented one of the more elegant features of general relativity. The theory's equations were flexible enough to permit these exotic geometric structures. However, Einstein and Rosen's primary goal wasn't to describe cosmic tunnels or shortcuts through space. They were trying to solve a problem in particle physics. They wanted to eliminate singularities from their theory. The bridge structure was a means to that end, a geometric way to describe particles without invoking point-like concentrations of mass and energy. From a modern perspective, their particle model didn't work out. Quantum mechanics, despite Einstein's discomfort with it, proved to be the correct framework for describing fundamental particles. But the geometric structure they described, the bridge connecting two regions of spacetime, would take on a life of its own. Other physicists would pick up where Einstein and Rosen left off, exploring the properties of these bridges not as models of particles, but as potential features of spacetime in their own right. The Einstein-Rosen bridge had a fascinating geometric property. If you could visualize it using an embedding diagram, a way of representing curved spacetime in a more intuitive form, it would look like two funnels connected at their narrowest points. Imagine two megaphones placed end to end, their narrow ends touching. The outside of each funnel would represent ordinary three-dimensional space, curving inward toward the connection. The throat where they meet would be the bridge itself. This visualization helps convey the structure, but it's important to remember that it's only a representation. The actual Einstein-Rosen bridge exists in four-dimensional spacetime, not in 3 dimensions plus a special embedding space. The embedding diagram is a tool for human intuition, a way to picture something that fundamentally exists in higher dimensions than we can directly visualize. The bridge described by Einstein and Rosen was static and symmetric. It didn't rotate. It didn't change with time. It simply connected two asymptotically flat regions of spacetime, meaning that far from the bridge, in either direction, spacetime would become increasingly flat and normal. The curvature and unusual geometry were concentrated near the throat. One crucial detail about the Einstein-Rosen bridge wasn't fully explored in their original paper: whether anything could actually travel through it. Could a particle, or a light beam, or a spacecraft pass from one region of spacetime to the other by traversing the bridge? Or was the bridge merely a mathematical connection, present in the equations, but not traversable in practice? This question wouldn't be seriously addressed for several more decades. In the immediate aftermath of Einstein and Rosen's paper, the physics community had other concerns. World War II was approaching. Many physicists would be drawn into war work, developing radar systems and, eventually, nuclear weapons. The Einstein-Rosen bridge remained a curious mathematical structure, noted in papers and textbooks, but not the subject of intensive study. After the war, as physics resumed its peacetime pace, researchers began revisiting the exotic predictions of general relativity. Black holes, still not called by that name, were being studied more carefully. The expansion of the universe, first discovered by Edwin Hubble in the late 1920s, was being investigated more deeply, and the strange bridge-like structures, allowed by Einstein's equations, were waiting for someone to explore them more thoroughly. The mathematics of the Einstein-Rosen bridge was clear. The structure existed as a valid solution to the field equations. What remained unclear was its physical significance. Did such bridges exist in nature? If so, where might they be found? And could they serve any practical purpose, or Were they merely geometric curiosities with no connection to the real universe? These questions would require new mathematical tools and new physical insights to answer. The geometry of the bridge needed to be analysed in detail. The behaviour of light and matter near the throat needed to be understood. And crucially, the stability of the structure needed to be examined. Would an Einstein-Rosen bridge, if it formed somehow, persist over time? Or would it collapse, pinching off before anything could pass through? The answers to these questions would come slowly, pieced together by physicists over decades. Each new insight would add to our understanding, revealing both the potential and the limitations of these remarkable structures. But all of that lay in the future. For now, in 1935, the Einstein-Rosen bridge was simply an intriguing feature of a beautiful theory, a mathematical bridge waiting for someone to determine whether it led anywhere real. The legacy of Einstein and Rosen's work extended far beyond their original intentions. They had set out to solve a problem in particle physics and ended up creating the mathematical foundation for what would become one of physics' most captivating concepts. Their bridge would evolve in the hands of later researchers into something far grander than they imagined. A potential shortcut across the cosmos, a tunnel through space-time, a structure that might one day, if we're extraordinarily lucky and clever, allow travel between distant stars. For nearly 2 decades after Einstein and Rosen published their paper, the bridge they described remained primarily a mathematical curiosity. Physicists were aware of it, certainly. It appeared in textbooks and research papers as an interesting feature of general relativity, but it hadn't yet captured the broader imagination of the physics community. It was one solution among many, one strange prediction in a theory full of strange predictions. That began to change in the 1950s, largely due to the work of one person, John Archibald Wheeler. Wheeler was a theoretical physicist at Princeton University, with a talent for vivid imagery and colourful language. He had a gift for taking abstract mathematical concepts and making them accessible, even exciting. He coined the term black hole in 1967, replacing the awkward earlier phrase, gravitationally, completely collapsed object. Before Wheeler, physicists spoke about these objects in technical jargon. After Wheeler, everyone called them black holes. In the 1950s, Wheeler became interested in the topological properties of spacetime. Topology is the branch of mathematics concerned with properties that remain unchanged under continuous deformations. A coffee cup and a donut have the same topology because each has one hole, and you could theoretically deform one shape into the other without tearing or gluing. Wheeler wondered whether space-time itself might have a complex topology, full of handles, tunnels, and other structures invisible at large scales, but potentially significant at quantum scales. Wheeler was particularly intrigued by the Einstein-Rosen bridge. He recognized that while Einstein and Rosen had presented it as a model for particles, the structure itself was far more interesting than its original purpose suggested. Here was a genuine tunnel through space-time, a connection between distant regions permitted by the very equations that governed gravity. Wheeler decided it needed a better name than Einstein-Rosen bridge, something more evocative, something that captured the essence of what it was. In 1957, Wheeler coined the term wormhole. The name was inspired by an analogy. Imagine an apple with a worm inside it. From the worm's perspective, living on the surface of the apple, the quickest path between 2 points might not be along the curved surface, but through a tunnel bored through the apple's interior. The worm's tunnel would be a shortcut, a 3-dimensional path that's shorter than the 2-dimensional route across the surface. Similarly, a wormhole in space-time would be a shortcut through the 4-dimensional geometry of the universe. 2 points that appear distant when measured through ordinary 3-dimensional space might be much closer when measured through the wormhole. The three-dimensional beings living in ordinary space would see two separate locations, possibly light years apart. But the wormhole would connect them directly, offering a path that bypasses the intervening space. Wheeler's terminology caught on immediately. Wormhole was perfect, simple, memorable, and evocative. It conveyed the essential idea without requiring pages of mathematics. Soon, physicists everywhere were speaking about wormholes, and the concept began appearing in popular science writing and even science fiction. But Wheeler wasn't content merely to give these structures a catchy name. He wanted to understand their properties in detail. Were wormholes stable? Could they exist for any appreciable time? Could matter pass through them? These were questions that Einstein and Rosen hadn't fully addressed in their original paper, and Wheeler set out to answer them. To do this, Wheeler needed to examine the dynamics of wormholes, not just their static geometry. He needed to understand how they would evolve over time. The Einstein-Rosen bridge described by Einstein and Rosen was a snapshot, a single moment frozen in the mathematics. But in reality, spacetime is dynamic. Masses move, gravitational fields change, and structures evolve. Wheeler wanted to know what would happen to a wormhole as time progressed. He enlisted the help of Robert Fuller, one of his graduate students at Princeton. Together, Wheeler and Fuller performed a detailed analysis of the Schwarzschild wormhole, the simplest type of wormhole described by the Einstein-Rosen solution. They published their results in 1962, and what they found was both fascinating and discouraging. Wheeler and Fuller discovered that the Schwarzschild wormhole was unstable. Not just slightly unstable, but catastrophically so. According to their calculations, if such a wormhole existed, it would pinch off almost instantly, closing the connection between its two mouths before anything could pass through. Even light, travelling at the universe's speed limit, couldn't make it from one end to the other before the throat collapsed. The problem was gravitational. The wormhole's own gravity worked against it. The throat wanted to collapse, to seal itself off. There was nothing to hold it open, no force counteracting the inward pull. The result was a structure that might exist briefly, but would be useless as a passage or shortcut. It was like a tunnel that collapses the moment you try to enter it. This was disappointing news for anyone hoping wormholes might serve as cosmic shortcuts. The mathematics permitted their existence, but the physics seemed to forbid their use. A Schwarzschild wormhole couldn't be traversed. It would snap shut before you could blink, let alone send a spacecraft through it. Wheeler and Fuller's work seemed to close the door on practical wormholes. If the simplest type of wormhole was unstable, what hope was there for more complex versions? The consensus in the physics community shifted. Wormholes remained interesting as mathematical objects, as solutions to Einstein's equations, but they were thought to have no physical relevance. They were curiosities, not actual features of our universe. Yet even as that consensus formed, physicists continued studying wormholes for theoretical reasons. They remained useful as teaching tools, helping students understand the geometry of curved spacetime. They appeared in thought experiments exploring the limits of general relativity, and they persisted in science fiction, where writers imagined advanced civilizations using wormholes to traverse the galaxy despite what the physics seemed to say about their stability. The period from the 1960s through the early 1980s was a quiet time for wormhole research. Physicists worked on other problems: black hole thermodynamics, the expansion of the universe, the unification of fundamental forces. Wormholes remained in the background, acknowledged but not actively investigated. The instability problem seemed insurmountable, but science rarely moves in straight lines. A problem that seems impossible in one decade might become solvable in the next, not because the problem changes, but because our understanding deepens. New mathematical tools emerge, new physical insights appear. Connections between seemingly unrelated fields reveal unexpected solutions. And so it would be with wormholes. The breakthrough would come not from studying general relativity in isolation, but from bringing in ideas from quantum mechanics, the other great pillar of 20th century physics. Quantum mechanics, the theory Einstein had been so uncomfortable with, would provide the key to stabilizing wormholes. The union of quantum theory with general relativity, always a difficult and incomplete marriage, would open new possibilities for these cosmic tunnels. But before we can understand how quantum mechanics saved the wormhole concept, we need to understand in more detail why wormholes are unstable in the first place. We need to delve deeper into the problem that Wheeler and Fuller identified to see exactly what forces work against a wormhole's existence and what might be needed to overcome them. To understand why wormholes collapse, we need to think carefully about what happens to spacetime near the throat. The throat is the narrowest part of the wormhole, the connection point between its two mouths. In the Schwarzschild wormhole that Wheeler and Fuller analysed, the throat has a certain radius, a minimum circumference that any path through the wormhole must pass. Now imagine a beam of light travelling through the wormhole. As the light approaches the throat from one side, the curvature of spacetime affects its path. The light's trajectory follows geodesics, the straightest possible paths through curved spacetime. Near the throat, these geodesics converge, coming closer together as the geometry narrows. This convergence is governed by something called the Rauschord-Hurry equation, a fundamental result in general relativity that describes how geodesics evolve. The equation relates the convergence or divergence of geodesics to the curvature of spacetime, which in turn is determined by the distribution of matter and energy. For ordinary matter and energy, the Rauschord-Hurry equation predicts that geodesics will converge, that light rays travelling parallel to each other will be bent toward each other by gravity. This is why gravity focuses light, why a massive object can act as a gravitational lens, bending light from distant sources and creating multiple images or arcs in the sky. Now think about light travelling through a wormhole. As it enters the throat from one side, the geodesics converge, as expected. But then something remarkable must happen. After passing through the throat, as the light emerges on the other side, the geodesics must diverge again, spreading apart as the geometry widens back out into normal space. This divergence is the problem. For geodesics to diverge after converging, the curvature of spacetime near the throat must be different from what ordinary matter produces. Normal matter causes convergence. Something else, something with very unusual properties, would be needed to cause divergence. That something is what physicists call exotic matter. Exotic matter isn't just rare or strange. It's matter with fundamentally different gravitational properties from anything we encounter in everyday life. Specifically, exotic matter must have negative energy density relative to the vacuum. In technical terms, it must violate what's called the null energy condition, a principle stating that the energy density measured by any observer moving at the speed of light must be non-negative. This might sound like abstract mathematical jargon, but it has physical meaning. Ordinary matter has positive energy density and attracts other matter through gravity. Exotic matter would have negative energy density and would exert a repulsive gravitational effect. Instead of pulling things together, it would push them apart. This repulsive effect is exactly what's needed to keep a wormhole's throat open. Think of the throat of a wormhole like a tunnel through a mountain. Ordinary gravity, the weight of the rock overhead, wants to collapse the tunnel. Without support beams or some other structure holding the rock back, the tunnel will cave in. Similarly, the ordinary matter and energy in and around a wormhole create gravitational effects that want to collapse the throat. What's needed is something to hold it open, something to counteract that inward pull. Exotic matter would be that support structure. Its negative energy density would create a repulsive gravitational effect, pushing outward against the throat's tendency to collapse. With enough exotic matter properly distributed around and through the throat, a wormhole could theoretically be stabilized, held open indefinitely rather than snapping shut in an instant. But here's the challenge. We don't know if exotic matter exists in sufficient quantities or in the right form to stabilize a macroscopic wormhole. Quantum mechanics suggests that something like exotic matter can exist in very limited circumstances. The quantum vacuum, rather than being truly empty, is filled with fluctuations, temporary particles popping in and out of existence. In certain configurations, these fluctuations can produce negative energy densities. The most famous example is the Casimir effect, predicted by Dutch physicist Hendrik Casimir in 1948. Place two uncharged metal plates very close together in a vacuum. Quantum fluctuations in the electromagnetic field between the plates are constrained by the boundary conditions imposed by the plates. Certain wavelengths of these fluctuations can't exist between the plates because they don't fit. Outside the plates, however, all wavelengths are possible. The result is that the energy density between the plates is lower than the energy density outside them. This creates a net attractive force pulling the plates together. The attraction has been measured experimentally and matches the predictions of quantum field theory beautifully. The region between the plates effectively has negative energy density relative to the vacuum outside. This proves that negative energy densities can exist, at least in principle, and in specific quantum mechanical setups. The question is whether they can exist in the quantities and configurations needed to stabilize a wormhole. The Casimir effect involves incredibly tiny forces acting over microscopic distances. A wormhole, even a small one by cosmic standards, would be enormously larger, perhaps requiring a throat radius measured in meters or kilometers. The amount of exotic matter needed would be correspondingly vast. Estimates vary depending on the specific wormhole geometry being considered, but physicists have calculated that stabilizing even a small wormhole might require negative energy equivalent to the mass of a planet or star. Where would such enormous quantities come from? Could quantum processes somehow be amplified to macroscopic scales? Or are wormholes forever limited to microscopic sizes, if they can exist at all? These questions led to a period of intensive theoretical work in the 1970s and early 1980s. Physicists explored various scenarios. Could exotic matter be generated by some unknown quantum process? Could rotating or charged wormholes be more stable than the simple Schwarzschild version? Could modifications to general relativity, perhaps incorporating effects from quantum gravity, change the stability requirements? One interesting possibility that emerged was that the amount of exotic matter needed might depend on the wormhole's geometry. Not all wormhole solutions require the same distribution of exotic matter. Some configurations might be more economical, requiring less negative energy than others. This opened the door to optimizing wormhole designs, finding geometries that would be most stable with the least amount of exotic matter. Another area of investigation was whether exotic matter might naturally exist somewhere in the universe. Could there be astrophysical processes that generate negative energy densities? Could the interiors of black holes or the extreme conditions near neutron stars, or the violent environment of the early universe, have produced pockets of exotic matter? These are speculative ideas, but they're not entirely without merit. The universe has surprised us before with phenomena we didn't expect. The stability problem also raised deeper questions about the nature of spacetime itself. General relativity is a classical theory, meaning it doesn't incorporate quantum mechanics. At very small scales, quantum effects become important, and we need a quantum theory of gravity to describe what happens. Such a theory doesn't exist yet, at least not in a complete and tested form, but its eventual discovery might change our understanding of wormhole stability. Perhaps at quantum scales, tiny wormholes appear and disappear constantly, part of the quantum foam that some physicists believe makes up spacetime at the smallest distances. These quantum wormholes would be far too small to use for travel, but they might play a role in fundamental physics, connecting different regions of spacetime at the Planck scale, the unimaginably tiny distance where quantum gravitational effects become dominant. Or perhaps a full quantum theory of gravity would show that macroscopic wormholes can't exist at all, that the classical solutions we've been discussing are artifacts of treating gravity classically when quantum effects should be included. This would be disappointing for anyone hoping to use wormholes for travel, but it would still be valuable knowledge, telling us something important about the nature of spacetime. For now, the stability problem remains. We know that simple wormholes collapse. We know that exotic matter could stabilize them. We know that exotic matter can exist in quantum mechanical systems, at least in limited ways. What we don't know is whether nature provides exotic matter in the quantities and forms needed for macroscopic, traversable wormholes. That's the central uncertainty in the entire field of wormhole physics. Yet despite this uncertainty, research continued. Physicists are nothing if not persistent. If a problem seems impossible today, that just means we haven't yet found the right approach, the right tool, the right insight. And sometimes the breakthrough comes from an unexpected direction, from someone asking a slightly different question or applying a technique from a different field. In the case of wormholes, that breakthrough would come in the late 1980s, when a physicist asked not whether wormholes could exist, but what they would look like if we wanted to use them. Before we can fully appreciate the breakthrough that came in 1988, we need to understand exotic matter more deeply. What exactly is it? How does it differ from ordinary matter? And what does quantum mechanics tell us about its possible existence? In physics, when we talk about matter, we're usually referring to stuff with positive energy density. A kilogram of water, a block of iron, a cloud of hydrogen gas, these all have positive energy. They contribute to the curvature of spacetime in a particular way, creating what we recognize as attractive gravity. They pull other objects toward them. The more massive an object, the stronger its gravitational pull. Energy density is energy per unit volume. Ordinary matter has positive energy density. If you measure the energy in a given volume of space containing matter, you get a positive number. Even seemingly empty space has energy density. The quantum vacuum, despite having no particles in it, still has an energy density associated with quantum fluctuations. This vacuum energy is thought to be positive, contributing to what we now call dark energy, the mysterious component driving the universe's accelerating expansion. Exotic matter would have negative energy density. This doesn't mean it has less energy than empty space. It means it has less energy than the vacuum itself. Its presence would lower the total energy of a region of spacetime below what it would be if that region were completely empty. This is a strange concept because we don't encounter anything like it in everyday life. Everything we interact with has positive energy compared to the vacuum. The gravitational effect of negative energy density would be repulsive rather than attractive. Instead of pulling nearby objects closer, exotic matter would push them away. This repulsive gravity is precisely what's needed to hold open a wormhole's throat. The throat naturally wants to collapse due to the normal attractive gravity of space-time curvature. Exotic matter threading through the throat would counteract this tendency, pushing outward and stabilizing the structure. Now, The critical question becomes, can negative energy densities actually exist, or are they merely mathematical possibilities with no physical realization? This is where quantum mechanics enters the picture, offering both hope and limitation. Quantum field theory, which combines quantum mechanics with special relativity, describes particles as excitations of underlying fields. The electromagnetic field pervades all of space, and a photon is a quantum of that field, a discrete packet of electromagnetic energy. Similarly, there are fields for electrons, quarks, and all other fundamental particles. Even in their ground states with no particles present, these fields have energy due to quantum fluctuations. These fluctuations arise from the Heisenberg uncertainty principle, which places limits on how precisely certain pairs of properties can be simultaneously known. One form of the uncertainty principle relates energy and time. It tells us that over sufficiently short time intervals, energy can fluctuate by large amounts without violating conservation laws. Virtual particles can briefly pop into existence, borrow energy from the vacuum, and then annihilate before the universe notices the debt. In most circumstances, these quantum fluctuations produce positive energy density on average. But in special configurations, the fluctuations can be constrained in ways that produce negative energy densities relative to the unconstrained vacuum. The Casimir effect is the clearest example. The metal plates restrict which virtual photons can exist between them. Longer wavelengths don't fit. This restriction means fewer virtual particles between the plates than outside them, resulting in lower energy density between the plates. The Casimir force has been measured with extraordinary precision. Experiments using micro-electromechanical systems have confirmed the predicted attraction between conducting surfaces at the sub-micrometer scale. The effect is real, demonstrable, and well understood theoretically. It proves that quantum mechanics permits negative energy densities in specific contexts. Other quantum phenomena also involve negative energy. The Hawking radiation emitted by black holes, predicted by Stephen Hawking in 1974, involves negative energy falling into the black hole while positive energy escapes to infinity. The net energy of the black hole decreases, causing it to evaporate slowly over time. The infalling negative energy is essential to this process. Squeezed states of light, created in quantum optics experiments, represent another example. By manipulating the quantum fluctuations in one component of the electromagnetic field, physicists can create states where energy density in certain regions becomes negative relative to the vacuum. These effects are small and fleeting, but they're real and have been observed experimentally. So negative energy exists in quantum systems. The challenge is scaling it up. The Casimir effect involves forces measured in nanonewtons acting over distances measured in nanometers. A wormhole might need forces billions of times stronger acting over distances billions of times larger. That's an extraordinary extrapolation, and it's far from clear that it's possible. Physicists have explored various schemes for concentrating negative energy. Could you use mirrors or other devices to channel quantum fluctuations in useful ways? Could you exploit the enormous energy densities present near black holes or neutron stars? Could there be astrophysical processes that naturally generate regions of negative energy on large scales? One intriguing proposal involves what's called a quantum inequality. Quantum field theory places limits not just on whether negative energy can exist, but on how much negative energy can be concentrated in a given region for a given time. The more negative energy you want to collect, the briefer the duration over which you can maintain it, or the larger the spatial region you must spread it across. These quantum inequalities suggest that, while negative energy is possible, there are fundamental limits to how much you can use. For wormholes, this is potentially devastating news. If quantum inequalities prevent the accumulation of sufficient negative energy to stabilize a macroscopic wormhole, then such wormholes simply can't exist, regardless of our technological capabilities. Nature would forbid them through the fundamental laws of quantum physics. However, quantum inequalities aren't fully understood yet. They're derived from quantum field theory in flat spacetime, but wormholes involve strongly curved spacetime where the rules might be different. The interaction between quantum mechanics and gravity remains mysterious. We don't have a complete theory of quantum gravity, and until we do, there will be uncertainties about what's truly possible. Some physicists have proposed that exotic matter might not need to have negative energy density everywhere. Perhaps it could have negative energy in some places and positive energy in others, with the distribution carefully arranged to stabilize the wormhole while satisfying quantum inequalities. This would be like building an arch where each stone is under compression, held in place by the precise arrangement of forces. The wormhole would be a delicate balance of positive and negative energy densities, stable as long as the configuration is maintained. Another possibility is that the exotic matter needed might not be matter in the usual sense at all. Perhaps it could be a field, something like the Higgs field, that gives particles their masses, but with different properties. A scalar field with the right potential energy curve could produce the negative energy density needed near the wormhole throat. This field wouldn't be something you could scoop up and hold. It would be a feature of spacetime itself, a background condition that enables the wormhole's existence. Speculative theories beyond the standard model of particle physics sometimes include fields with exotic properties. String theory, for example, predicts numerous additional fields beyond those we've discovered. Some of these might have the properties needed to stabilize wormholes. This is highly speculative, of course. String theory remains unproven, and even if it's correct, we don't know whether the fields it predicts actually exist in our universe or whether they have the right properties. The exotic matter problem connects to broader questions in physics about the nature of vacuum energy and dark energy. The cosmological constant, which describes the energy density of empty space, is positive and causes the universe's expansion to accelerate. But we don't understand why it has the value it does or what physical field or mechanism produces it. Understanding dark energy might shed light on whether negative energy densities are possible on cosmological scales. There's also the question of whether exotic matter would be stable. Even if you could create it somehow, would it persist? Or would it decay quickly into ordinary matter, releasing energy in the process? The stability of exotic matter is as important as its creation. A wormhole held open by exotic matter that only lasts microseconds wouldn't be very useful. Despite all these challenges and uncertainties, the existence of negative energy in quantum systems gives researchers hope. It proves that the concept isn't nonsense, that nature does permit energy densities below the vacuum in at least some circumstances. The question shifts from, is it possible, to under what conditions is it possible, and can those conditions be achieved? This shift in perspective was crucial for the next developments in wormhole physics. Instead of asking whether wormholes could exist given what we know about exotic matter, physicists began asking the reverse question. If we wanted to build a traversable wormhole, what properties would the exotic matter need to have? This engineering approach, treating the wormhole as a design problem rather than just a mathematical curiosity, would lead to the breakthrough that reinvigorated the entire field. The stage was set for someone to take the next step, to carefully work through the requirements for a traversable wormhole and explore whether those requirements might, even in principle, be achievable. That someone would be Kip Thorne and his student Michael Morris, working at Caltech in the late 1980s. Their work would transform wormholes from mathematical abstractions into serious objects of scientific study. In 1985, Carl Sagan was writing a science fiction novel called Contact. The story involved a scientist who discovers a message from an alien civilization and eventually travels through a system of tunnels connecting distant parts of the galaxy. Sagan wanted his novel to be scientifically accurate, or at least plausible, so he reached out to Kip Thorne, a renowned physicist at the California Institute of Technology and an expert on general relativity. Sagan's initial idea involved his protagonist travelling through a black hole to reach distant stars. Thorne immediately saw the problem with this scenario. A black hole isn't a tunnel. It's a one-way trap. Anything that falls past the event horizon, the point of no return, is inevitably pulled toward the singularity at the centre. There's no way out, no tunnel to emerge from on the other side. The traveller would be crushed by tidal forces and destroyed. But Thorne didn't just point out the problem, he offered a solution. He suggested that Sagan use a wormhole instead. Unlike a black hole, a wormhole could, in principle, provide a traversable passage from one location to another. It was still speculative, still requiring exotic physics, but it wasn't as immediately lethal as a black hole. Sagan took the advice and incorporated a wormhole network into his novel. This conversation sparked something in Thorne's mind. He realized that while physicists had studied wormholes for decades, no one had carefully worked out what a traversable wormhole would actually require. Wheeler and Fuller had shown that simple wormholes collapse. Everyone knew exotic matter would be needed for stability. But what exactly were the requirements? Could you specify the properties a wormhole would need to have to be usable for travel? Thorne decided to investigate. He enlisted one of his graduate students, Michael Morris, and together they set out to design a traversable wormhole from first principles. They weren't asking whether such a structure could exist or how you might create one. They were asking a more basic question. If you wanted a wormhole that humans could travel through safely, what would it look like? What constraints would it need to satisfy? Morris and Thorne published their results in 1988 in the American Journal of Physics. The paper, titled Wormholes in Spacetime and Their Use for Interstellar Travel, a tool for teaching general relativity, was explicitly pedagogical. It was meant to help students understand general relativity by working through a concrete example. But it was also groundbreaking. It provided the first detailed blueprint for a traversable wormhole. They started with basic requirements. The wormhole should connect two distant regions of space, with mouths in both locations and a throat linking them. It should be traversable, meaning travellers could pass through in both directions without being crushed or trapped. The trip through the throat should take a reasonable amount of time, not millions of years, and the structure should be stable, at least long enough for round-trip travel. To satisfy these requirements, Morris and Thorne needed to specify the spacetime geometry carefully. They chose a spherically symmetric static solution, meaning the wormhole doesn't rotate and doesn't change with time. This kept the mathematics manageable while still capturing the essential physics. The key geometric feature was the shape of the throat. In an embedding diagram, where you visualize the wormhole as two funnels connected at their narrow ends, the throat is the minimum circumference. Morris and Thorne showed that for the wormhole to be traversable, the throat needs to flare outward as you move away from the minimum circumference in both directions. This flaring is essential. Why is flaring important? Because it's directly connected to the focusing of geodesics we discussed earlier. For light rays or particle trajectories to pass through the throat and emerge on the other side, they must diverge after passing through the minimum circumference. If the throat didn't flare outward, geodesics would converge and intersect, creating a caustic, a place where the geometry becomes badly behaved and matter and energy concentrate. The flaring condition requires exotic matter. To see why, Morris and Thorne used the Einstein field equations, which relate the geometry of spacetime to the distribution of matter and energy. They showed that for the throat to flare outward, the energy density along certain directions must be negative. Specifically, measured in the radial direction through the throat, the energy density must violate the null energy condition. This wasn't a surprise. Wheeler and Fuller had already shown that exotic matter was needed for stability, but Morris and Thorne quantified the requirement precisely. They calculated how much exotic matter would be needed, how it would need to be distributed, and what constraints this placed on the wormhole's geometry. They also considered the tidal forces a traveller would experience. Tidal forces arise because gravity varies with position. Your feet, being slightly closer to a massive object than your head, experience slightly stronger gravity. In extreme gravitational fields, like near a black hole, this difference can be enormous, enough to stretch and tear apart anything that ventures too close, a process gruesomely called spaghettification. Morris and Thorne wanted their wormhole to be gentle, to produce tidal forces weak enough that a human traveller could pass through safely. This placed additional constraints on the geometry. The throat needed to be large enough and smooth enough that the curvature didn't create lethal tidal stresses. For a wormhole with a throat radius of a few kilometres, the tidal forces could be kept to tolerable levels, comparable to what you might experience on Earth's surface. They also explored how long the trip through the wormhole would take. This depends on the geometry of the throat and how far the two mouths are separated in ordinary space. Morris and Thorne showed that the travel time through the wormhole could be much shorter than the time it would take to travel the same distance through ordinary space. This is the essence of the wormhole as a shortcut. The distance through the throat is shorter than the distance through normal space. Imagine 2 points on opposite sides of the galaxy, 30,000 light-years apart, as measured through ordinary space. A traveller taking the conventional route would need at least 30,000 years, even moving at the speed of light. But if a wormhole connected those 2 points, the distance through the throat might be only a few kilometres. A traveller moving through the wormhole at ordinary speeds could make the trip in minutes. This dramatic shortcut is possible because the wormhole's geometry allows the two mouths to be far apart in three-dimensional space, while being close together along the path through the throat. It's like folding a piece of paper so two distant points touch, then cutting a hole through both layers. The distance through the hole is tiny, while the distance across the unfolded paper remains large. Morris and Thorne also addressed another crucial issue: horizons. A horizon is a boundary where space-time becomes so curved that escape becomes impossible. Black holes have event horizons. Once you cross the event horizon of a black hole, you can never return. All paths lead inward. A traversable wormhole, by definition, should not have horizons. Travellers must be able to enter from either mouth, pass through the throat, and emerge from the other mouth, reversing direction if they choose. The absence of horizons requires careful engineering of the space-time geometry. The curvature must be arranged so that no point along the path through the wormhole traps travellers. This again connects to the exotic matter distribution. The negative energy density needs to be positioned and concentrated in specific ways to keep the geometry horizon-free. The Morris-Thorne paper included explicit mathematical expressions for a wormhole metric, a formula describing the geometry of space-time around their designed wormhole. This metric satisfied all their requirements: traversable, stable with exotic matter, gentle tidal forces, no horizons. It provided a concrete example that researchers could study and build upon. The paper was a sensation in the physics community. Suddenly, wormholes weren't just abstract solutions to Einstein's equations or unstable structures that collapsed instantly. They were potential engineering projects, structures that could, in principle, be designed and optimized. Physicists began exploring variations on the Morris-Thorne design, looking for geometries that required less exotic matter or that had other desirable properties. One important follow-up question was how much exotic matter would actually be needed. Morris and Thorne's original paper didn't calculate the total amount required to stabilize their wormhole, just the distribution and density in different regions. Later analyses tried to quantify this. The results varied depending on assumptions, but typical estimates suggested that even a small wormhole might require exotic matter equivalent to the mass of a planet or star, if not more. This sounds impossibly large, and it might well be, but it's worth remembering that we're talking about negative energy, not positive mass. The exotic matter wouldn't weigh billions of tons in the usual sense. It would have negative energy density, creating repulsive gravitational effects. The challenge isn't lifting or moving it, but creating it in the first place. Some researchers looked for ways to minimize the exotic matter requirement. Could you design a wormhole geometry that achieves traversability with less exotic matter? Various proposals emerged. Some suggested very thin shells of exotic matter concentrated near the throat's minimum circumference, with normal matter elsewhere. Others explored whether rotation or electric charge could reduce the requirements. Visser, a physicist at Washington University, extended Morris and Thorne's work significantly. He explored a variety of wormhole geometries, including those with flat space asymptotically far from the mouths, and those embedded in expanding or contracting universes. He showed that many different designs could satisfy the basic requirements for traversability, each with its own balance of exotic matter needs and geometric properties. The Morris-Thorne revolution didn't prove that traversable wormholes exist. It didn't show how to create one or where to find exotic matter. What it did was demonstrate that such structures are consistent with the laws of physics as we understand them. They're not forbidden by general relativity. The question shifted from, are they possible, in principle, to does nature provide the ingredients needed to build them? This shift in perspective energized the field. Throughout the 1990s and 2000s, papers on wormhole physics appeared regularly. Researchers explored their properties, designed new geometries, considered observational signatures, and investigated connections to other areas of physics. Wormholes became respectable objects of scientific study, not just science fiction tropes. The Morris-Thorne paper also influenced physics education. It became a standard example in advanced general relativity courses, a case study showing how to apply the Einstein field equations to a concrete problem. Students learned to think about spacetime engineering, about designing geometries with specific properties. This pedagogical impact shouldn't be underestimated. A generation of physicists grew up comfortable with wormholes as theoretical objects, familiar with their properties and limitations. Perhaps most importantly, the Morris-Thorne work showed the power of asking the right question. Instead of wondering whether wormholes could exist in some vague, general sense, they asked a specific, targeted question. What would a usable wormhole need to look like? This engineering mindset, treating fundamental physics as a design problem, would prove fruitful in many contexts beyond wormholes. It's a reminder that sometimes progress comes not from new data or new theories, but from new ways of thinking about old problems. The Morris-Thorne wormhole, elegant as it is, represents just one possible design. General relativity permits many different wormhole geometries, each with its own properties and requirements. To understand the full landscape of wormhole physics, we need to explore this diversity. to see what variations are possible and how they differ from one another. The simplest classification divides wormholes into two broad categories: intra-universe wormholes and inter-universe wormholes. An intra-universe wormhole connects two different locations within the same universe. This is what most people imagine when they think about wormholes as shortcuts through space. Both mouths are in our universe, just far apart, with the throat providing a bridge between them. An inter-universe wormhole would connect our universe to a completely different universe, a separate bubble of space-time with potentially different physical laws and properties. These are much more speculative. We don't even know for certain that other universes exist, let alone whether wormholes could connect to them. But they arise naturally in some solutions to Einstein's equations, so they're at least mathematically possible. Within the intra-universe category, there are further distinctions. The Schwarzschild wormhole, the type Wheeler and Fuller analysed, is the simplest. It's non-rotating, uncharged, and spherically symmetric. Its two mouths are identical. The geometry is static, unchanging with time. As we've discussed, this type of wormhole is unstable, collapsing before anything can traverse it. The Morris-Thorne wormhole is a traversable version, stabilised by exotic matter. It shares the Schwarzschild wormhole's spherical symmetry and static nature, but the addition of exotic matter changes the geometry enough to keep the throat open. This makes it fundamentally different in terms of its physical properties and potential usefulness. Rotating wormholes add another layer of complexity. In 1963, Roy Kerr found a solution to Einstein's equations describing a rotating black hole. The Kerr solution is more complicated than the Schwarzschild solution because rotation breaks spherical symmetry. The geometry depends not just on distance from the centre, but also on direction. The Kerr metric includes a parameter describing how fast the black hole spins. Interestingly, the Kerr solution also permits wormhole-like structures. In the mathematical description of a rotating black hole, there are multiple horizons, surfaces where the geometry behaves in particular ways. Between these horizons, the structure of spacetime allows, at least in principle, for passage from one region to another. However, these Kerr wormholes have serious problems. They're unstable, and they include regions with closed time-like curves, paths through spacetime that loop back on themselves, potentially allowing time travel with all its associated paradoxes. Charged wormholes are another possibility. The Reissner-Nordstrom solution describes a non-rotating black hole with electric charge. Like the Kerr solution, it includes multiple horizons and wormhole-like features in the geometry. Again, these structures are unstable and have pathological properties that make them unsuitable for travel. Some researchers have explored hybrid designs, combining rotation and charge. These become mathematically intricate, but they're valid solutions to Einstein's equations. Each combination of properties produces a different spacetime geometry with unique characteristics. Cataloguing all these possibilities is an ongoing project in theoretical physics. Another important distinction is between thin shell wormholes and volume-filling wormholes. In a thin shell design, the exotic matter is concentrated in a very thin layer, perhaps just at the throat's minimum circumference. Everywhere else, the geometry is similar to ordinary spacetime, possibly filled with normal matter or even empty. This design is appealing because it minimizes the amount of exotic matter needed. Thin shell wormholes were studied extensively by Visser and others. The idea is to take two pieces of ordinary spacetime, cut them, and glue them together with a thin layer of exotic matter at the junction. The exotic matter acts like a gasket, sealing the connection and providing the negative energy density needed for stability. The mathematics of thin shell wormholes involves techniques from junction conditions in general relativity, determining how spacetime geometries can be smoothly matched across boundaries. Volume-filling wormholes, by contrast, have exotic matter distributed throughout a larger region. The Morris-Thorne design falls into this category, although the exotic matter isn't uniformly distributed. The density and distribution of exotic matter affect the geometry and the stability of the wormhole. Finding the optimal distribution, one that minimizes the total exotic matter needed while ensuring stability and traversability, is a complex optimization problem. Some wormhole designs include what are called absurdly benign wormholes. These are geometries crafted to be as gentle as possible for travelers. The tidal forces are kept extraordinarily low, the throat is wide and smooth, and the transit time is short. These represent the ideal from an engineering perspective, maximally safe and efficient. Of course, they may also require the most exotic matter or have other trade-offs that make them less practical in other ways. There are also dynamical wormholes, structures that change with time. Most of the wormholes we've discussed are static, their geometry fixed. But a wormhole could, in principle, evolve. Its throat might expand or contract. The mouths might move relative to each other. These time-dependent solutions are mathematically more challenging to analyse, but they're important for understanding how wormholes might form or decay. One particularly interesting class involves traversable wormholes in cosmological contexts, embedded in universes that are, themselves, expanding or contracting. The Friedman, Lemaitre, Robertson, Walker spacetimes, which describe homogeneous and isotropic cosmologies, can be joined via wormhole throats. These cosmological wormholes connect different regions of an expanding universe, or possibly different expanding universes entirely. Lorentzian wormholes are the main focus of most research. These are wormholes in ordinary spacetime, where the geometry is described by the Lorentzian metric of general relativity. But there are also Euclidean wormholes, which appear in certain quantum gravity calculations. Euclidean wormholes are mathematical constructs where time is treated as an imaginary number, converting the spacetime geometry into a purely spatial one. They're important in some approaches to quantum cosmology, but don't represent structures you could actually travel through. Another exotic possibility is the Möbius wormhole, a wormhole with a twist. Imagine traversing the throat and emerging from the other mouth, but in a universe where left and right are reversed, a mirror image of the space you left. This represents a non-orientable topology, a geometry that includes a reflection. Whether such structures could actually exist is unclear, but they're mathematically interesting and show just how flexible general relativity can be. Some researchers have explored wormholes with multiple mouths, structures where more than two regions of spacetime are connected. These would be like hubs, with multiple tunnels converging at a central throat. The geometry becomes complicated, and the exotic matter requirements increase, but there's nothing in principle preventing such configurations. There's also the question of size. Could wormholes exist at microscopic scales? Some quantum gravity theories predict that spacetime at the Planck scale, about 10 to the negative 35 meters, might be filled with quantum foam, a seething froth of tiny wormholes constantly appearing and disappearing. These quantum wormholes would be far too small to traverse, but they might affect physical processes at fundamental levels. At the other extreme, could wormholes exist at galactic or even cosmological scales? A wormhole with mouths separated by millions or billions of light years would be a truly cosmic structure. Its formation would require exotic matter on scales hard to imagine, but again, general relativity doesn't forbid it. We simply don't know if nature builds structures this large. The diversity of wormhole types reflects the richness of general relativity as a theory. Each solution, each geometry, each variation tells us something about how space-time can be curved and connected. Even if none of these structures exist in reality, they serve as laboratories for exploring the limits and capabilities of Einstein's equations. This catalogue of possibilities also helps guide observational searches. If wormholes exist, they might come in various forms, each with its own observational signature. Knowing what types are possible helps astronomers know what to look for. A rotating wormhole might produce different gravitational effects than a static one. A thin shell wormhole might have different mass distributions than a volume-filling one. These distinctions matter when trying to detect or rule out wormholes observationally. The study of wormhole types is ongoing. New solutions continue to be found, and old solutions continue to be better understood. Each paper adding to this literature is like adding a new species to a field guide, cataloguing the biodiversity of possible space-time structures. And like biological diversity, this mathematical diversity reveals principles and patterns, showing us what's fundamental and what's merely contingent in the architecture of the cosmos. Perhaps the most mind-bending aspect of wormholes isn't their potential as shortcuts through space, but their possible use as time machines. Under certain circumstances, a wormhole could allow travel not just to distant locations, but into the past. This possibility raises profound questions about causality, free will, and the nature of time itself. The connection between wormholes and time travel was first seriously explored in the late 1988 by Kip Thorne and his collaborators, including Michael Morris and another graduate student, Ulva Yurtseva. They published a paper examining whether a traversable wormhole could be converted into a time machine, and if so, what constraints physics might place on such devices. The key insight is that while both mouths of a wormhole are connected through the throat, they can be at different positions, in time as well as space. Imagine creating a wormhole with both mouths initially at rest relative to each other. Now take one mouth and accelerate it to a high speed, then bring it back. Due to time dilation, a consequence of special relativity, less time passes for the moving mouth than for the stationary one. Time dilation is a well-established effect. When an object moves at speeds approaching the speed of light, time for that object slows down relative to stationary observers. This has been confirmed countless times with atomic clocks on aircraft and satellites. An astronaut travelling at high speed ages more slowly than people on Earth. Now imagine one mouth of a wormhole making this high-speed journey. Inside the throat, the two mouths remain connected, but outside they become separated in time. If you wait long enough, the difference could become substantial. The travelling mouth might be hours, days, or even years behind the stationary mouth in time. Here's where time travel becomes possible. Step through the stationary mouth, traverse the throat, and emerge from the travelling mouth. But that travelling mouth is in the past, relative to where you started. You've travelled backward in time. Then, outside the wormhole, travel through ordinary space back to the stationary mouth. You arrive in your own past before you left. This creates what's called a closed time-like curve, a path through space-time that loops back on itself. You could, in principle, meet your younger self, deliver a message to your past self, or even prevent yourself from entering the wormhole in the first place. This is the classic time travel paradox. If you travel back and prevent your past self from time travelling, then you never travelled back, so you couldn't prevent yourself, and so on. These paradoxes have names. The grandfather paradox imagines travelling back and accidentally causing your grandfather's death before your parent was born, thus preventing your own existence. The bootstrap paradox involves information or objects that have no origin, looping endlessly through time. These aren't just philosophical puzzles. They suggest that something in physics must prevent time travel or at least prevent the paradoxes from arising? Thorne and his colleagues explored this question carefully. Could physics somehow prevent the conversion of a wormhole into a time machine? Or if time machines are possible, are there principles that prevent paradoxes? They found that creating closed, time-like curves with a wormhole might be possible, but it faces significant obstacles. One problem involves the build-up of radiation. As a wormhole approaches the configuration needed for time travel, quantum fluctuations in the fields threading through the throat get amplified. These fluctuations could become enormous, creating a burst of high-energy radiation that destroys the wormhole just as it's about to become a time machine. This effect, sometimes called the chronology protection mechanism, was studied by Stephen Hawking. Hawking proposed what he called the chronology protection conjecture. He suggested that the laws of physics conspire to prevent the formation of closed time-like curves, at least at macroscopic scales. Whenever you try to create a time machine, quantum effects step in to sabotage the attempt. Radiation builds up, space-time fluctuations become infinite, or some other catastrophe occurs, preventing the formation of the closed time-like curve. The mathematics behind chronology protection is complex and not fully settled. It involves quantum field theory in curved spacetime, an area where calculations are difficult and physical intuition is uncertain. Some studies suggest that radiation buildup would indeed destroy a wormhole time machine. Others suggest that the effect might not be strong enough, or that clever engineering could circumvent it. There's also the question of what happens if closed time-like curves do form. Would paradoxes actually occur, or does the structure of spacetime somehow enforce consistency, allowing only self-consistent timelines? The consistency approach says that if time travel is possible, only outcomes that don't create paradoxes can occur. If you travel back to kill your grandfather, something will always prevent you. Your gun will jam, you'll change your mind, you'll arrive at the wrong location, something will intervene to maintain consistency. This isn't a mystical force. It's just that in a space-time with closed time-like curves, only self-consistent solutions to the equations of motion exist. This idea was formalized by Igor Novikov and others as the self-consistency principle, or the Novikov principle. It states that the only solutions to the laws of physics that can occur are those that are globally self-consistent. If an event would create a paradox, that event simply doesn't happen, not because some external force prevents it, but because the equations governing physics in curved spacetime don't permit inconsistent solutions. The Novikov principle is elegant, but it raises its own questions. How exactly does consistency get enforced? If you try to shoot your grandfather, what specific physical mechanism makes the gun jam? It seems to require a kind of cosmic conspiracy, where all the random quantum fluctuations and microscopic events align to ensure the macroscopically self-consistent outcome. Some physicists find this unsatisfying. Others see it as a natural consequence of the mathematical structure of general relativity. In space-time with closed time-like curves, cause and effect become intertwined in complex ways. The future influences the past, which influences the future, creating a web of mutual causation. In such a structure, only globally consistent patterns can exist. There are also many worlds interpretations of time travel. In the many worlds view of quantum mechanics, every quantum measurement causes the universe to split into multiple branches, one for each possible outcome. Applied to time travel, this would mean that when you travel back and change the past, you don't alter your original timeline. Instead, you create a new branch where the past is different. In this scenario, you could kill your grandfather, but you'd be killing him in a different timeline, not the one you came from. Your original timeline, where you existed and built the time machine, remains unchanged. You simply aren't in it anymore. You've moved to a parallel history. This eliminates paradoxes because you never affect your own past, only the past of a different universe. The many worlds approach to time travel is intellectually satisfying in some ways, but it comes with the usual baggage of many worlds interpretations. It requires accepting that every quantum event spawns countless new universes, and it doesn't really address what happens with macroscopic time travel in a deterministic setting. Beyond these theoretical considerations, there's the practical question of whether wormhole time machines could ever be built. Creating the time difference between the mouths requires moving one at relativistic speeds, energies far beyond our current capabilities. It also requires having a traversable wormhole in the first place, which requires exotic matter we don't know how to produce. Even if these challenges could be overcome, there's the question of causality violation in the broader universe. If one civilization creates a time machine, the effects could ripple outward. Information from the future could spread throughout the galaxy, affecting countless worlds and events. The universe would become a tangled web of causal loops, past and future, intertwined in ways difficult to comprehend. Some physicists argue that the absence of time travelers from our future is evidence that time machines are impossible. If they were possible, and ever will be possible, shouldn't we have encountered travelers from the future by now? This argument, while intuitive, has loopholes. Perhaps time machines can only access times after their creation, so we wouldn't see travelers from before the first machine is built. Perhaps advanced civilizations choose not to visit our particular time and place. Perhaps they're subtle enough that we don't notice them. The physics of time travel also connects to deeper questions about the nature of time itself. Is time fundamentally different from space? The equations of physics often treat them symmetrically. Time is just another dimension in spacetime, with different geometric properties than spatial dimensions, but not fundamentally distinct. If space can be curved and connected in complex ways, why not time? Yet time feels different. We remember the past but not the future. Entropy increases in one temporal direction but not the other. Cause precedes effect. These asymmetries suggest something special about time, something that distinguishes it from space in ways the geometric formulation of general relativity doesn't capture. The thermodynamic arrow of time, pointing in the direction of increasing entropy, is particularly important. Entropy is a measure of disorder, and the second law of thermodynamics states that entropy tends to increase in closed systems. A broken egg doesn't spontaneously reassemble. Smoke doesn't unmix with air. Heat flows from hot to cold, not the reverse. If time travel were possible, could you violate the second law? Could you return to a state of lower entropy, effectively reversing the thermodynamic arrow? The relationship between time travel and thermodynamics is subtle. Some analyses suggest that consistency can be maintained even with closed time-like curves, that the entropy of the entire system, including the time traveler and their interactions, still increases overall. Others suggest tensions between time travel and thermodynamic principles. The quantum mechanics of time travel adds yet another layer of complexity. Quantum mechanics already has peculiar features involving time. The equations are time reversible at a fundamental level, yet measurements produce irreversible outcomes. Quantum entanglement creates correlations that seem to transcend time ordering in certain contexts. Adding time travel to quantum mechanics produces a formalism called post-selected quantum mechanics, where the future can influence the past in probabilistic ways. David Deutsch, a physicist at Oxford, explored quantum mechanics with closed time-like curves in detail. He showed that you can formulate a consistent quantum theory even in the presence of time travel. The key is allowing quantum superpositions that include self-consistent loops. A particle could travel back, interact with its past self, and produce a superposition of outcomes, all of which are consistent when properly calculated. This quantum approach doesn't eliminate the strangeness of time travel, but it does show that mathematical consistency can be maintained. The universe wouldn't break if closed time-like curves existed. It would just become more subtle, more quantum, with probabilities rather than definite outcomes governing the interactions between past and future. All of these considerations, from the physics of wormhole time machines to the paradoxes they might create, from chronology protection to quantum consistency, paint a picture of time travel as profoundly uncertain. We don't know if it's possible. We don't know if physics prevents it or permits it. We have theoretical frameworks suggesting both possibilities. What we do know is that if time travel is possible, it would be constrained by the same physical laws that govern everything else. It wouldn't be arbitrary or lawless. The universe would find a way to accommodate it, either through consistency principles, many worlds branching, chronology protection, or some mechanism we haven't yet conceived. The connection between wormholes and time travel has made them even more fascinating to physicists and the public alike. A wormhole isn't just a shortcut through space. It's potentially a doorway to other times, a structure that could let you witness history or glimpse possible futures. This elevates wormholes from interesting to profound, from useful to transformative. Yet it also increases the stakes for understanding them. If wormholes could be time machines, then their creation would be one of the most consequential events in cosmic history. It would change the nature of causality itself, at least locally. This adds urgency to questions about their feasibility and about the constraints physics might place on their use. The interplay between space and time in wormhole physics is a reminder that these aren't separate concepts, but aspects of a unified whole. Space-time is the stage, and wormholes are one of the ways that stage can be folded, twisted, and connected in unexpected ways. Whether those connections include loops in time, as well as bridges across, space remains one of the deepest mysteries in theoretical physics. In recent decades, physicists have uncovered surprising connections between wormholes and quantum mechanics, links that suggest these seemingly disparate areas of physics might be deeply related. These connections involve quantum entanglement, black hole information paradoxes, and speculative ideas about the nature of space-time itself at the most fundamental level. The story begins with quantum entanglement, a phenomenon where two particles become correlated in ways that can't be explained by classical physics. When particles are entangled, measuring a property of one particle instantaneously determines the corresponding property of the other, regardless of the distance separating them. Einstein famously called this spooky action at a distance because it seemed to involve faster-than-light connections. Quantum entanglement has been experimentally verified countless times. It's a real feature of quantum mechanics, well understood mathematically, even if still conceptually puzzling. Entangled particles behave as a single system, with correlations that persist across space. The quantum state describing them is non-local, meaning it can't be factored into separate states for each particle. In 2013, physicists Juan Maldacena and Leonard Susskind proposed a remarkable conjecture connecting quantum entanglement to wormholes. They suggested that quantum entanglement and geometric connections in spacetime might be two descriptions of the same underlying phenomenon. Specifically, they proposed that two entangled black holes are connected by a wormhole, a geometric bridge in spacetime. This idea is often summarized by the equation ER equals EPR. ER stands for Einstein-Rosen, referring to the wormhole bridge Einstein and Rosen described. EPR stands for Einstein-Podolsky-Rosen, referring to a famous paper where Einstein and collaborators discussed quantum entanglement. The equation suggests these two concepts, wormholes and entanglement, are equivalent or at least closely related. At first glance, this seems absurd. Entanglement is a quantum phenomenon involving correlations between particle properties. Wormholes are geometric structures in spacetime. How could they possibly be the same thing? The connection emerges from deep theoretical work in quantum gravity and string theory, particularly the ADS-CFT correspondence. The ADS-CFT correspondence is a mathematical relationship between a theory of gravity in a certain type of curved spacetime called anti-de Sitter space and a quantum field theory without gravity living on the boundary of that space. This correspondence, discovered by Juan Maldacena in 1997, has been extraordinarily fruitful, providing insights into both quantum mechanics and gravity. Within this framework, entanglement in the boundary quantum field theory corresponds to geometric connections in the bulk gravitational theory. When particles on the boundary are entangled, there's a wormhole-like structure in the bulk connecting the regions where those particles are located. The more entangled the particles, the stronger and more stable the geometric connection. This suggests a profound reinterpretation of what entanglement means. Rather than being a purely quantum phenomenon with no geometric interpretation, entanglement might actually create structure in spacetime. Two entangled particles might be connected by a tiny wormhole, too small to traverse but geometrically real nonetheless. The correlations we observe as entanglement might be manifestations of these microscopic connections. If this idea is correct, it would unify quantum mechanics and general relativity in a deep way. It would show that the geometry of spacetime emerges from quantum entanglement, that space itself is woven from quantum correlations. This is a radical suggestion, but it's supported by detailed calculations in specific theoretical models. The ER equals EPR conjecture also addresses a famous puzzle called the black hole information paradox. When matter falls into a black hole, information about its quantum state seems to be lost. This violates quantum mechanics, which requires that information be conserved in all processes. Stephen Hawking's work on black hole radiation made this paradox acute, showing that black holes evaporate over time, radiating particles that seem to carry no information about what fell in. If entangled black holes are connected by wormholes, this might resolve the paradox. Information wouldn't be lost because it could be encoded in correlations between the interior of the black hole and the exterior, maintained by the wormhole connection. This is speculative, and the details are still being worked out, but it's a promising avenue for resolving one of theoretical physics' deepest puzzles. The relationship between entanglement and geometry extends beyond black holes. Some researchers have proposed that all of spacetime might emerge from quantum entanglement. In this view, the three dimensions of space aren't fundamental. They're emergent properties arising from the pattern of entanglement in an underlying quantum system. Space would be like temperature, a large-scale property that emerges from microscopic quantum behavior. This idea, sometimes called emergent spacetime, is being actively explored in quantum gravity research. If successful, it would mean that the geometry we perceive, the distances and angles that define our three-dimensional world, are secondary features. The primary reality would be a quantum system with no inherent spatial structure, and space would arise from how parts of that system are entangled with each other. Wormholes, in this picture, would be regions where entanglement is particularly strong, creating shortcuts through the emergent spatial geometry. They would be natural features of emergent spacetime, appearing wherever quantum correlations are concentrated. This provides a completely different perspective on wormholes, not as exotic objects requiring special construction, but as generic features of how space emerges from quantum mechanics. These ideas remain highly theoretical. We're nowhere near experimentally testing whether entanglement creates microscopic wormholes or whether spacetime is emergent. The energy scales and sizes involved are far beyond current technology, but the mathematical connections are compelling, and they suggest that our understanding of both quantum mechanics and gravity is incomplete, that there are deeper principles waiting to be discovered. Another quantum aspect of wormholes involves their behavior at very small scales. Some theories of quantum gravity predict that spacetime at the Planck scale, about 10 to the negative 35 meters, has a foam-like structure. At these tiny distances, quantum fluctuations become so strong that spacetime itself becomes turbulent, with virtual wormholes constantly appearing and disappearing. This quantum foam, if it exists, would be unobservable directly. The distances are too small, the timescales too brief, but it might have indirect effects on particle physics and cosmology. Virtual wormholes could allow particles to hop from one point in space to another, affecting probabilities and interactions in subtle ways. They might contribute to vacuum energy or alter the behavior of quantum fields. John Wheeler, who coined the term wormhole, was one of the first to speculate about quantum foam. He imagined space-time at the smallest scales as a seething sea of geometry, with topology constantly changing. Wormholes would be part of this dynamic landscape, threads connecting different regions of the foam. Wheeler called this space-time foam, or quantum foam, and he believed it held clues to unifying quantum mechanics and gravity. Modern quantum gravity research has explored these ideas more rigorously. Loop quantum gravity, one approach to quantizing gravity, describes space-time as built from discrete units called loops. The connections between these loops create a network structure that might, at larger scales, appear as continuous space. Wormholes in this picture would be special configurations of the loop network, paths through the graph that connect distant nodes. String theory, another approach to quantum gravity, also accommodates wormholes. In string theory, fundamental particles are replaced by one-dimensional strings vibrating in higher dimensional space. The equations of string theory permit wormhole solutions, including exotic types that don't appear in classical general relativity. These string-theoretic wormholes might play roles in particle physics or cosmology, connecting different regions of the higher dimensional space. The quantum mechanics of traversable wormholes raises additional questions. If you send a quantum particle through a wormhole, does it maintain its quantum coherence? Quantum coherence is the property that allows particles to exist in superpositions and exhibit interference. Decoherence, the loss of coherence due to environmental interactions, is what makes quantum systems appear classical. A wormhole, even a traversable one, might cause decoherence because the particle interacts with the exotic matter threading the throat and with the curved geometry. If decoherence is strong, quantum information might be scrambled or lost during transit. This would limit the usefulness of wormholes for quantum communication or quantum computing applications. Alternatively, a carefully designed wormhole might preserve quantum coherence, allowing quantum states to be transmitted intact. This would be valuable for quantum communication, potentially enabling instantaneous transmission of quantum information between distant locations. However, the no-signaling theorem in quantum mechanics prevents faster-than-light communication, so even a wormhole couldn't be used to send messages instantaneously in a way that violates causality. The relationship between quantum mechanics and wormholes also touches on the measurement problem. In quantum mechanics, measurement causes wave function collapse, turning superpositions into definite outcomes. What counts as a measurement is still debated. Could a wormhole act as a measuring device? If a particle in superposition enters a wormhole, does the geometry itself collapse the wave function? These questions don't have clear answers yet. They sit at the intersection of quantum mechanics, general relativity, and quantum information theory, an area where our theoretical tools are still developing. But they highlight how wormholes, even as theoretical constructs, help us probe the boundaries of our understanding, revealing where our current theories are incomplete or inconsistent. The quantum connections to wormholes also raise possibilities for experiments, at least in tabletop analogues. Physicists have created artificial wormhole-like systems in condensed matter physics and quantum optics. These aren't actual spacetime wormholes, but they mimic some of their properties using quantum systems. Studying these analogues might reveal general principles about how quantum mechanics and geometry interact. For example, researchers have created holographic wormholes in quantum computers, simulating the dynamics of particles in a spacetime with wormhole connections. These simulations, while limited, provide testable predictions and help validate the theoretical frameworks. They're a way to explore wormhole physics in the lab, even without exotic matter or curved spacetime. The quantum nature of wormholes also connects to the holographic principle, the idea that all the information in a volume of space can be encoded on its boundary. This principle, inspired by black hole thermodynamics, suggests that spacetime might be fundamentally two-dimensional, with the three-dimensional world we experience being a holographic projection. In a holographic universe, wormholes would connect different regions of the two-dimensional boundary. The three-dimensional bulk geometry would emerge from the entanglement structure of the boundary theory. This is closely related to the ADS-CFT correspondence and the ER equals EPR conjecture. All these ideas form a web of connections suggesting deep links between quantum information, entanglement, and spacetime geometry. As we drift through these quantum connections, a picture emerges of wormholes as more than just tunnels through space. They're quantum objects, deeply intertwined with the principles of quantum mechanics. They might be manifestations of entanglement, features of emergent spacetime, elements of quantum foam. They challenge us to think beyond classical geometry, to imagine space and time as quantum phenomena with their own uncertainty and superposition. This quantum perspective on wormholes is still being developed. New papers appear regularly, proposing connections, testing hypotheses, exploring implications. The field is active and evolving, with insights from string theory, quantum information, and cosmology all contributing. The ultimate resolution might require a complete theory of quantum gravity, something we don't yet have, but the progress so far is encouraging. It's a reminder that even the most exotic predictions of general relativity, structures like wormholes that seem impossibly strange, might find their place in a deeper theory. The strangeness might dissolve, revealing simplicity underneath. Or the strangeness might deepen, leading to even more surprising connections. Either way, the journey of discovery continues, guided by mathematics, experiment, and the human drive to understand. If wormholes exist in our universe, how would we know? What observational signatures would they produce? These questions have driven a fascinating area of research where physicists and astronomers consider how to detect something that might not exist, using tools and techniques at the cutting edge of modern science. The first challenge is that we don't know what wormholes would look like from the outside. Unlike black holes, which have well-defined event horizons and predictable effects on nearby matter and light, wormholes could come in many varieties, each with different properties. A wormhole's mouths might be massive or nearly massless, large or small, static or moving. Depending on these properties, the observational signatures could vary widely. One approach is to look for gravitational effects. A wormhole mouth would have mass, or at least would curve spacetime in characteristic ways. This curvature would affect the motion of nearby objects. Stars or gas clouds orbiting near a wormhole mouth would follow paths determined by the spacetime geometry. By observing these motions, astronomers could potentially infer the presence of a wormhole. However, distinguishing a wormhole from other massive objects is difficult. A wormhole mouth might produce gravitational effects similar to a black hole or a concentration of dark matter. You'd need additional signatures to confirm it's specifically a wormhole and not something else. One such signature might be the lack of an event horizon. A wormhole mouth, unlike a black hole, doesn't trap light. Material could orbit very close to the mouth without being inevitably pulled in. Gravitational lensing provides another detection method. When light passes near a massive object, its path bends due to spacetime curvature. This can create multiple images of background sources, arcs or rings, depending on the alignment. Astronomers routinely use gravitational lensing to study galaxies, galaxy clusters, and black holes. A wormhole would also act as a gravitational lens, but the lensing pattern might differ from that of a black hole or ordinary matter concentration. The exact pattern depends on the wormhole's geometry. Some researchers have calculated what lensing by various wormhole types would look like. In certain configurations, wormholes might produce distinctive features, such as negative lensing, where images are distorted in unusual ways, or secondary images appearing in unexpected locations. Detecting these subtle differences would require high-resolution observations and careful modelling. Current telescopes might not have sufficient sensitivity to distinguish wormhole lensing from other types, but future instruments, particularly in radio astronomy and with space-based telescopes, might achieve the necessary precision. Another potential signature involves gravitational waves. When two massive objects orbit each other and eventually merge, they emit gravitational waves, ripples in spacetime itself. These waves have been detected by LIGO, the Laser Interferometer Gravitational Wave Observatory, and other instruments. The detections have opened a new window on the universe, allowing astronomers to observe events involving black holes and neutron stars. If wormholes exist and can merge with each other, or with black holes, they would produce gravitational waves. The waveforms, the patterns of oscillation in the detected signal, would depend on the properties of the merging objects. A wormhole merger might produce waveforms distinct from black hole mergers, potentially allowing identification. Researchers have simulated what wormhole mergers might look like gravitationally. The results suggest that, in some cases, the signals would indeed differ from black hole mergers. Features such as echoes, repeating patterns in the gravitational wave signal after the main event, might indicate exotic structures like wormholes rather than ordinary black holes. Searching for these echoes in LIGO data is an ongoing effort. However, interpreting gravitational wave signals is complex. The data is noisy, and many factors affect the waveforms. Claiming a detection of a wormhole based on gravitational waves would require extremely strong evidence, carefully ruling out alternative explanations. So far, no confirmed wormhole detections have been made through this method, but the searches continue. Electromagnetic signatures offer another avenue. If matter falls into a wormhole mouth, it might emit radiation during the accretion process. Unlike a black hole, where material inevitably crosses the event horizon and disappears, material near a wormhole might pass through the throat and emerge from the other mouth. This could create unusual patterns of emission and absorption. For example, if one mouth of a wormhole is in a dense region with lots of gas and dust, and the other mouth is in an empty region of intergalactic space, material flowing through the wormhole might create a visible stream. Astronomers might observe gas apparently disappearing in one location and appearing in another, with no obvious connection through ordinary space. This would be suspicious and warrant closer investigation. Accretion disks, the swirling disks of material that form around massive objects, might also look different around wormholes than around black holes. The innermost stable circular orbit, the closest distance at which material can orbit without falling in, would be determined by the spacetime geometry. For some wormhole configurations, this could differ from the black hole case, affecting the disk's appearance and emission spectrum. Searching for these electromagnetic signatures requires knowing where to look. If wormholes are rare, randomly searching the sky would be inefficient. Targeted searches near objects that already seem anomalous, such as unexplained sources of X-rays or gamma rays, might be more productive. Alternatively, surveys that cover large areas of sky, like those conducted by the upcoming Legacy Survey of Space and Time at the Vera Rubin Observatory, might serendipitously discover signatures of wormholes. There's also the possibility that wormholes could be detected through their effects on cosmic rays. Cosmic rays are high-energy particles, mostly protons, that bombard Earth from space. If cosmic rays pass through a wormhole, they might gain or lose energy in characteristic ways. Analysing the energy spectrum and arrival directions of cosmic rays might reveal anomalies consistent with wormhole transit. This method is speculative and faces significant challenges. Cosmic rays are deflected by magnetic fields as they travel through space, obscuring their origin points. Distinguishing wormhole effects from other astrophysical processes would be difficult, but it's another potential avenue worth considering, especially if other methods fail to produce detections. Primordial wormholes, structures that might have formed in the early universe, could leave imprints on the cosmic microwave background radiation. The CMB is the afterglow of the Big Bang, a faint glow of microwave radiation coming from all directions in the sky. Tiny fluctuations in the CMB's temperature and polarization encode information about the early universe's structure. If wormholes existed in the early universe, they might have affected how matter and radiation were distributed. These effects could create specific patterns in the CMB fluctuations. Analysing CMB data from satellites like Planck and future missions could potentially reveal these signatures, though disentangling them from other cosmological effects would be challenging. Another detection strategy involves looking for the absence of expected phenomena. For example, if a massive object shows no signs of an event horizon, no point of no return, it might be a wormhole rather than a black hole. Techniques for testing whether black hole candidates have event horizons are being developed. These include looking for light echoes from material near the event horizon and studying the shadows cast by the objects against background light. The Event Horizon Telescope, a global network of radio telescopes that produced the first images of black hole shadows, could potentially distinguish between black holes and wormhole mouths. A wormhole might cast a different shadow or allow light to pass through where a black hole would not. These differences might be subtle, requiring exquisite observational precision, but they represent another tool for detection. There's also the intriguing possibility of communication through wormholes. If an advanced civilization has created traversable wormholes, they might use them for communication or travel. We might detect signals passing through wormholes or observe spacecraft entering one location and emerging from another. This is highly speculative and ventures into SETI territory, the search for extraterrestrial intelligence, but it's not entirely without merit. Looking for wormholes is complicated by not knowing how common they are, if they exist at all. If wormholes are abundant, detection might be straightforward. we might simply not have recognized what we're seeing. If wormholes are extremely rare, we might search for centuries without finding one. If they don't exist, we'll never find convincing evidence, though ruling out their existence completely would be nearly impossible. Despite these challenges, the search is worthwhile. Detecting a wormhole would be one of the most significant discoveries in the history of science. It would confirm exotic predictions of general relativity, reveal new physics, and potentially open pathways to exploring the universe in ways previously confined to imagination. Even null results, consistently failing to detect wormholes despite sensitive searches, would be valuable, constraining theories and guiding future research. The combination of gravitational wave astronomy, electromagnetic surveys, lensing studies, and theoretical modelling provides a multifaceted approach. As technology improves and data accumulates, our ability to detect or rule out wormholes will strengthen. The next few decades might bring clarity to questions that have lingered for nearly a century since Einstein and Rosen first described their bridge. For now, wormholes remain hidden if they exist at all. They wait in the mathematical equations, in the possibilities permitted by general relativity, in the speculations of physicists and the dreams of science fiction writers. Whether they're real or merely theoretical constructs, the search for them pushes the boundaries of what we can observe and understand, and that journey itself is part of the grand adventure of science. Wormhole physics in the 21st century is a vibrant field, drawing researchers from general relativity, quantum field theory, string theory, and cosmology. The questions have evolved from "do wormholes exist?" to more nuanced explorations of their properties, constraints, and potential roles in fundamental physics. Modern research uses increasingly sophisticated mathematical tools and computational simulations to probe these questions. One active area is numerical relativity, using supercomputers to solve Einstein's equations for complicated scenarios that resist analytical solution. Simulating the formation, evolution, and stability of wormholes requires enormous computational power. Researchers can model what happens when exotic matter is introduced into a region of spacetime, how the geometry responds, and whether stable wormhole configurations emerge. These simulations have revealed surprising details. For instance, some studies suggest that certain wormhole configurations might be more stable than previously thought, remaining open for extended periods under specific conditions. Others have explored how wormholes interact with surrounding matter and fields, how they respond to perturbations, and what happens during dynamical processes like collisions or mergers. Computational advances have also enabled exploration of wormhole interiors. What would a journey through a wormhole actually look like? By tracing light rays through the curved geometry numerically, researchers can create visualizations of the view from inside a wormhole. These images show distorted views of the two mouths, with light from both sides of the wormhole reaching the traveller simultaneously, creating surreal optical effects. Another modern research direction involves analog systems. Physicists have created wormhole analogues in various laboratory settings. These aren't actual space-time wormholes but systems that mimic certain properties of wormholes. For example, researchers have used metamaterials, engineered materials with unusual electromagnetic properties, to create structures that guide electromagnetic waves in ways analogous to how wormholes guide light. Other analogues use fluid dynamics. Sound waves in flowing fluids can behave analogously to light in curved spacetime. By carefully shaping fluid flows, researchers can create acoustic black holes and potentially acoustic wormholes. These analogues allow experimental exploration of phenomena that would be impossible to study in actual gravitational contexts. In 2022, researchers reported creating a holographic wormhole in a quantum computer. Using Google's Sycamore quantum processor, they simulated the dynamics of particles in a spacetime with wormhole-like connections, based on the ADS-TFT correspondence. While not a physical wormhole, this experiment demonstrated principles of quantum gravity and the ER equals EPR conjecture in a controlled setting. These analog systems are valuable for several reasons. They provide experimental testbeds for theoretical predictions. They help develop intuition about wormhole physics, and they sometimes reveal unexpected phenomena that inspire new theoretical work. While analogues can't replace observations of actual wormholes, they complement theoretical and observational efforts, creating a more complete picture. Research on exotic matter continues as well. Physicists explore whether there are unknown quantum fields or particles that could provide the negative energy densities needed to stabilize wormholes. Some studies focus on the Casimir effect and related phenomena, asking whether quantum vacuum fluctuations could be harnessed at macroscopic scales. Others investigate whether dark energy, the mysterious component driving cosmic acceleration, might have properties useful for wormhole stabilization. String theory research sometimes touches on wormholes. In string theory, the extra spatial dimensions beyond our familiar three could be connected in complex ways. Wormholes might exist in these higher dimensional spaces, providing shortcuts through dimensions we don't directly perceive. While highly speculative, these ideas expand the conceptual landscape of where and how wormholes might manifest. Loop quantum gravity, an alternative approach to quantizing gravity, also accommodates wormholes. In this framework, spacetime has a discrete structure at the smallest scales, built from quantum loops. Wormholes could be special configurations of this quantum geometry. Research explores whether loop quantum gravity predicts wormholes should exist, under what conditions and with what properties. Cosmological research considers whether wormholes might have played a role in the early universe. During the inflationary epoch, a period of exponential expansion shortly after the Big Bang, quantum fluctuations were amplified to cosmic scales. Perhaps some of these fluctuations created wormholes, which then grew along with the expanding universe. If so, there might be ancient wormholes scattered throughout the cosmos, remnants of the universe's violent birth. Some theories propose that our entire universe might be inside a wormhole connecting to a larger parent universe. This would reinterpret the Big Bang as the formation of a wormhole rather than the beginning of time itself. These ideas are difficult to test observationally, but they demonstrate how flexible our cosmological models can be when incorporating wormhole physics. Research on wormhole time machines remains active, though mostly theoretical. Papers continue exploring the consistency conditions for closed time-like curves, the quantum mechanics of time travel, and whether chronology protection is absolute or can be circumvented. While we're far from building time machines, understanding their theoretical constraints helps clarify the limits of general relativity and quantum mechanics. There's also growing interest in the thermodynamics of wormholes. Black holes have entropy, a measure of their information. There's also growing interest in the thermodynamics of wormholes. Black holes have entropy, a measure of their information content, proportional to the area of their event horizons. This black hole thermodynamics, developed by Hawking, Bekenstein, and others, has profound implications for quantum gravity. Do wormholes have similar thermodynamic properties? Can we assign them entropy and temperature? These questions connect to deeper issues about information, quantum mechanics, and the nature of spacetime. Some research suggests that wormholes might have entropy associated with the exotic matter threading them, or with quantum correlations between their mouths. If the ER equals EPR conjecture is correct, entanglement entropy might directly correspond to the entropy of the wormhole connecting entangled particles. This would unite concepts from quantum information theory with gravitational thermodynamics in a beautiful way. The energy requirements for creating wormholes have also been studied in detail. Even if exotic matter can be produced somehow, assembling enough of it and arranging it in the right configuration would require enormous energy. Some estimates suggest energies comparable to or exceeding the mass energy of entire stars. This places wormhole creation far beyond current or foreseeable human capabilities, firmly in the realm of advanced civilizations or natural astrophysical processes. However, other studies have explored whether smaller wormholes might be more feasible. A microscopic wormhole, too small for material objects but potentially useful for transmitting particles or information, might require far less exotic matter. While still requiring technology we don't have, the energy scales might be reachable by a sufficiently advanced civilization within the next few centuries. Research also considers whether natural processes might create wormholes. The extreme conditions in the early universe, near black hole singularities or in the cores of neutron stars, might generate exotic matter naturally. If so, wormholes might form without intelligent intervention as natural features of the cosmos. Detecting such natural wormholes would be extraordinarily exciting, revealing new physics and potentially offering shortcuts we could use even if we can't create wormholes ourselves. The field has also seen increased collaboration between theorists and observational astronomers. As detection techniques improve and data quality increases, theorists work closely with observers to identify potential signatures and develop search strategies. This synergy between theory and observation is essential for making progress on questions that are fundamentally empirical. Education and public outreach have become important aspects of wormhole research as well. The topic captures public imagination in ways few physics subjects do. Researchers write popular books, give public lectures, and engage with science communicators to share the latest developments. This public interest helps secure funding for research and inspires the next generation of physicists. Looking forward, several developments could transform wormhole physics in coming decades. Advances in gravitational wave astronomy, with more sensitive detectors and better data analysis, might reveal evidence of exotic objects like wormholes. The Event Horizon Telescope and similar initiatives might image structures around massive objects with sufficient detail to distinguish wormholes from black holes. Space-based gravitational wave detectors, like the proposed LISA mission, would access different frequency ranges and potentially detect signals invisible to ground-based instruments. Progress in quantum gravity might also clarify whether macroscopic wormholes can exist. A complete theory of quantum gravity would tell us definitively whether exotic matter can be produced in necessary quantities, whether wormholes are stable at quantum levels, and what role they play in fundamental physics. String theory, loop quantum gravity, or some yet undiscovered framework might provide these answers. Computational advances will enable ever more detailed simulations. Quantum computers might simulate quantum gravity effects that classical computers can't handle. Machine learning and artificial intelligence might identify patterns in observational data that humans would miss, potentially finding wormhole signatures in existing datasets. International collaborations will likely expand. Wormhole physics is inherently interdisciplinary, involving general relativity, quantum field theory, cosmology, astrophysics, and more. Large teams spanning multiple countries and institutions can tackle questions no single researcher or group could address alone. This collaborative approach mirrors developments in other areas of physics, from particle accelerators to space missions. The philosophical implications of wormhole research shouldn't be overlooked either. Questions about the nature of space and time, the relationship between quantum mechanics and gravity, and the ultimate structure of reality are deeply philosophical as well as scientific. Engaging with philosophers of science can help clarify conceptual issues and ensure rigorous thinking about what theories really mean. One intriguing possibility is that wormhole physics might connect to consciousness studies. Some interpretations of quantum mechanics give consciousness a role in wave function collapse. If wormholes involve quantum phenomena at macroscopic scales, could consciousness interact with them in special ways? This is highly speculative and not mainstream physics, but it represents the kind of boundary-pushing thinking that sometimes leads to unexpected insights. The economic and societal implications of wormhole discovery would be profound. If traversable wormholes were found or could be created, they would revolutionize space exploration, communication, and perhaps even energy production. The ability to travel instantly to distant parts of the galaxy would transform human civilization. Even the possibility of such technology reshapes how we think about our future. However, wormholes might also present risks. Time machine wormholes could destabilize causality. Wormholes connecting to dangerous regions of space could threaten civilizations. Unknown physics associated with wormholes might have unexpected consequences. These considerations have led some researchers to think about the ethics and safety of wormhole research, even though practical concerns remain far in the future. Science fiction continues to explore wormholes creatively, often ahead of scientific understanding. Stories and films featuring wormholes help shape public perception and sometimes inspire researchers to ask new questions. The dialogue between science fiction and science is productive, each enriching the other. Writers learn from physicists to make their stories more plausible, while physicists sometimes find that fiction has explored implications they hadn't considered. As research continues, wormhole physics exemplifies how theoretical investigation can proceed even when direct empirical testing is difficult or impossible. Mathematics, consistency requirements, and connections to other areas of physics provide guidance. While we'd love to observe a wormhole directly, the theoretical work proceeds regardless, deepening our understanding of spacetime and gravity. The coming decades will likely bring clarity to some questions about wormholes while raising new ones. That's how science progresses. Each answer opens new mysteries. Each discovery reveals how much remains unknown. Wormholes, whether they exist as physical objects or remain mathematical constructs, have already enriched our understanding of physics in countless ways. They've forced us to think more carefully about exotic matter, causality, quantum entanglement, and the nature of spacetime itself. Perhaps wormholes will be discovered tomorrow, revolutionizing our view of the universe. Perhaps they'll remain elusive for centuries. Perhaps they don't exist at all, and future physics will explain why general relativity's permission for these structures doesn't translate to physical reality. Whatever the answer, the journey of exploration has been worthwhile, expanding our knowledge and imagination in equal measure. As we come to the end of our journey through the story of wormholes, let's take a moment to reflect on what we've explored. We've travelled from Einstein's equations in 1915 to cutting-edge quantum gravity research in the 21st century. We've seen how a simple mathematical curiosity evolved into a rich field of study, touching nearly every area of theoretical physics. Wormholes began as an unexpected feature of general relativity, a bridge in Einstein and Rosen's equations that nobody quite knew what to do with. For decades they remained mathematical abstractions, interesting but seemingly irrelevant to the physical universe. Then Wheeler gave them a memorable name and began exploring their properties more seriously. Fuller and Wheeler showed that simple wormholes collapse, seemingly closing the door on their practical use. But physics rarely respects closed doors. The discovery that exotic matter could stabilize wormholes reopened the question. Morris and Thorne showed how to design traversable wormholes, transforming them from impossible to merely incredibly difficult. Subsequent research revealed connections to time travel, quantum entanglement, black hole thermodynamics, and the fundamental nature of spacetime. Today, wormholes occupy a fascinating position in physics. They are permitted by our best theory of gravity, but require exotic matter we don't know how to produce. They might exist naturally in the universe, or they might be purely theoretical constructs with no physical counterparts. They could be doorways to distant stars and other times, or they could be forever beyond our reach, tantalizing possibilities that nature ultimately denies. What makes wormholes so compelling isn't just their potential as shortcuts through space and time. It's what they represent about the nature of scientific inquiry. They show us that mathematics can lead us to ideas we'd never conceive through intuition alone. They demonstrate that the universe might be far stranger than we imagine, structured in ways that defy common sense, yet obey elegant mathematical laws. Wormholes also remind us of the limits of our knowledge. We have a beautiful theory of gravity and general relativity, and a beautiful theory of the quantum world in quantum mechanics, but we don't yet know how to fully combine them. The questions surrounding wormholes about exotic matter and quantum consistency and the nature of space-time point directly at this gap in our understanding. Answering these questions will require new physics, new insights that go beyond our current theories. There's something poetic about wormholes as well. They're bridges, connections between distant realms. In a universe that often seems vast and empty, with light years separating stars and galaxies, wormholes represent the possibility of closeness, of connections transcending ordinary distance. They remind us that space itself might be more flexible than it appears, that the cosmos might be more intimately connected than the night sky suggests. Whether wormholes exist or not, thinking about them has been productive. The research has advanced our understanding of gravity, improved our mathematical techniques, and revealed unexpected connections between different areas of physics. The search for wormhole signatures has driven development of new observational tools and analysis methods. The speculative nature of the field has encouraged creative thinking and willingness to explore ideas at the boundaries of what's known. For those of us listening tonight, seeking rest and quiet wonder, wormholes offer something special. They're reminders that the universe still holds mysteries, that there are questions without answers, and possibilities yet unexplored. They invite us to imagine, to dream of journeys across the cosmos, of shortcuts through space and loops through time. They connect our small everyday lives to the grandest scales of cosmic structure. As you drift towards sleep, you might imagine standing at the mouth of a wormhole, looking into that tunnel through space-time. What would you see? Perhaps the stars of a distant galaxy, light years away, yet somehow close enough to touch. Perhaps the Earth of the past or future, a window into another time. Perhaps something entirely unexpected, a view that our current physics can't even describe. The mathematics says such structures are possible, permitted by the fundamental equations governing gravity. Whether nature chooses to realize these possibilities remains unknown. But the fact that they're possible at all, that the laws of physics allow such exotic and wonderful structures, tells us something profound about the universe we inhabit. We live in a cosmos governed by mathematics, described by equations of extraordinary beauty and power. Those equations, worked out by generations of physicists, contain within them possibilities that still amaze us. Wormholes are among those possibilities, bridges in the architecture of space-time, tunnels through the fabric of reality itself. So as we close this exploration, let's carry with us that sense of wonder. The universe might contain wormholes connecting distant stars. It might allow travel through time. It might be woven from quantum entanglement, with space itself emerging from correlations between fundamental particles. Or it might be simpler than we imagine, with wormholes remaining forever in the realm of mathematics and speculation. Either way, the journey of discovery continues. Each generation of physicists builds on the work of those before, asking new questions, developing new tools, pushing the boundaries of knowledge outward. Wormholes are part of that journey, waypoints in our exploration of how the universe works at its most fundamental level. Thank you for joining me on this journey through the story of wormholes. Thank you for your curiosity, your patience, and your willingness to explore ideas that stretch the imagination. If you enjoyed this gentle exploration of cosmic mysteries, a like and subscribe would help this channel continue bringing you more restful journeys through science and space. The universe awaits, full of wonders we've discovered and mysteries yet unsolved. Wormholes sit at the intersection of knowledge and imagination, mathematical precision and speculative wonder. Whether they're real or remain theoretical, they've enriched our understanding and expanded our sense of what might be possible. So rest now, and perhaps dream of bridges across the cosmos, of tunnels through space-time, of connections linking distant stars. Dream of a universe more flexible and strange than everyday experience suggests, where space can fold and time can loop, where the impossible becomes merely incredibly difficult. Dream of wormholes, those most elegant of cosmic shortcuts, waiting perhaps in the equations, perhaps in the stars, perhaps in futures yet to unfold. Sweet dreams, fellow travellers. Until next time, may your curiosity stay strong, your wonder remain vivid, and your dreams carry you across the vast reaches of space and time, through wormholes real or imagined, to places unknown and waiting to be discovered. Good night.